Today we'll look at an example of finding area between two curves using the integral. So, for example, let's find the area enclosed by y equal x squared and y equal x cubed. So always first sketch a picture. X squared looks something like this. And x cubed, remember, is up on the right. And down on the left. And so we're talking about this region right in here that's enclosed by the two curves. I'm going to shade that region. I always like to shade reminding myself that the underlying geometry of the integral is a bunch of rectangles. So whenever I shade a region, I don't just randomly shade it in. I like to make those marks as sort of a reminder of the underlying geometry of the theory there. So to set up our integral, we need two things. We need to know what are our limits of integration, and we need to know which function is bigger. So first of all, we need to know where this region ends, where it starts. So what are these 2 points? Now, these curves were familiar enough we can probably just look, and we know from graphing these through algebra what those points are. But in general, remember, to find those points of intersection, we'll set those two equal to each other. Let me label this guy here. This one was y equal x cubed. So setting those two equal, x squared equals x cubed. Gather everything to one side. And remember, a common algebra mistake is to just divide both sides by x squared to get rid of it. The problem with that is x could be 0. And remember, we can't divide by 0. So when you're trying to solve these polynomial equations, you want to always gather everything to one side and factor. So next, factor, x squared can come out. X minus 1, setting those equal to 0. We get x equals 0 and x equal 1. So we know that this point of intersection here is at 1, and this one's here at 0. All right, so we know where we're going to start. We know where we're going to stop. So we know our integral is from 0 to 1. Now, which one is bigger? Well, in this interval from 0 to 1, the green curve's the bigger one. That's x squared. Now, if you couldn't remember what these graphs looked like exactly, you could always test a point, right? Take a point halfway between, for example, x equal a half. If you plug a half into x cubed, you get 1/8. If you plug a half into x squared, you get 1/4. A fourth is bigger than an eighth. So just numerically, you know that's the bigger curve in there. So x squared is larger. X squared minus x cubed dx. Now all we have to do is apply the fundamental theorem of calculus, find our antiderivative, and plug in our limits. So we know that's 1/3 x cubed minus 1/4 x to the 4th, 0 up to 1. 1 into there. is a third minus a fourth. 0 into there is 0 minus 0. A third minus a fourth is a 12th. So this region in here has an area of 1/12. We didn't specify any units here, so I don't mind if you leave units off since we didn't specify whether this was inches, meters. You could, if you like, just say units squared. It is an area to remind yourself what kind of value you're talking about there. But unless we specify units, I'm okay with leaving the units off on the answer.